come across at the transmitter itself, right? We consider these to be independent, right? These two sources are independent. We deal them independently. When we discuss channel noise, we never discuss about quantization noise, and when we discuss quantization noise, we never discuss channel noise. Okay, so they are independent. We began with the channel noise. So we saw the receiver system, right, of a pulse code modulation, right, wave, right. We transmit the binary encoded PCM wave, transmit in the form of this S of t, right. But due to the noise, we find at the receiver it will be received as X of t. Now we assumed W of t as a additive white Gaussian noise with noise power spectral density n naught by 2, and it is assumed to be zero mean, and S of t is actually W of t, right. X of t is now a sample function of a random process capital X of t, right, and this signal X of t is passed through a matched filter, right. The output of matched filter is sampled at time t equal to t sub b. Now this t sub b is the duration of binary symbol, whether it is 0 or a 1. It's the duration of a binary symbol, and this results in the,
sir.
Yeah.
We can't see the PPT, sir.
Oh my God, I'm sorry. Oh, I have not shared it. Now,
Yes, sir.
Yes.
Yeah, thank you so much. Yeah, right. So S of t is the information signal, W of t is the noise signal. So it is additive white Gaussian noise adds up with the signal, resulting in a sample function of a random process X of t, right, and it is passed through a matched filter. Matched filter output is sampled every t sub b second, resulting in a, right, if we sample at t equal to t sub b, we get the maximum value, that is x1. Now this x1 is nothing but the random random value, right. Now this x1 is nothing but a sample value of a random variable x, right. So this x1 is a sample value of a random variable x1, which is again Gaussian random variable x1, which is again a Gaussian random variable. Now this x1 has to be passed through a decision device, and the decision device will estimate this x1 what it is for, right. We have discussed it in the last class, right. So how we got this? This is nothing but this diagram you can see, right. This is nothing but signal space diagram, right. So signal space diagram of PCM, right. We have come across this, right. So what is this 0 stands for, right. Suppose I take two signals, right, here. So S of t, we have two signals in S of t, that is S1 of t and S2 of t, right. We have discussed this in the last class. S1 of t corresponding to symbol 1, S2 of t corresponding to symbol 0, and it can be written as square root of Emax by square root of t sub b, and S2 of t, and this can be defined over a duration t sub b, right, and S2 of t can be defined as 0, right, 0 less than or equal to t, less than or equal to t sub b, right. So duration of the symbol 1 is t sub b, duration of symbol 0 is t sub b. This is what we have done in the last class, right. Last class we have assumed the PCM binary encoded PCM to be a unipolar NRZ format, in which symbol 1 can be represented as square root of Emax by square root of TB, and 0 is represented by 0, right? I mean, the symbol 0 is represented with 0 volts, and these two will lead to, right, will give us the function that is basis function, right? Phi of t is a basis function which is a unit energy signal, right? So I can define it as t sub b, right, over 0 less than or equal to t less than or equal to t sub b, right? So why I have taken 1 by root of t sub b? Because it has to be a unit energy signal, right? So you find at the receiver there is only one match filter. There is only one match filter, and the symbols are two, that is 0 and 1, right? Symbol 1 and 0, there are two symbols, not like you have seen likelihood function in the right, or rather in the bank of match filter or bank of correlators at the receiver, right? Why we get bank of correlators or bank of match filter at the receiver in the previous previous discussion, what you have seen in response of bank of correlators or match filter? Because the vector, so if I have n vectors, sorry, if I have a vector length is n, right, then I should go for n orthonormal, I mean n match filter. Here it is not so. There is only one basis function. One basis function means only one match filter. Okay, one basis function lead to only one match filter, right? So now the signal corresponding to symbol 1 is, right, S1 of t is nothing but square root of E max by t sub b, which is nothing but S11 phi 1 of t, and it is defined for 0 to t less than or equal t less than or equal to t sub b, and S2 of t is corresponding to symbol 0. It is nothing but 0 into 1 by t sub b, and it is for the duration of, right, t sub b, right? So the basis function is 1 by t sub b. That means we can represent these S1 of t and S2 of t as a linear combination of n orthonormal basis function. There is no n basis function here. There is only one basis function. That is why I can represent this S1 of t as one basis function, S2 of t also as one basis function, right? So now I can represent these S1 of t and S2 of t as a vector, right? So S2, vector S2 is nothing but 0. It is a scalar itself. Vector S1 is nothing but, it's a scalar itself, which is nothing but square root of E max, right? So now I can represent these vectors in single dimensional vector space. Now this is a single dimensional vector space, okay, phi 1, right? Single dimensional vector space in which only one axis I have, or one basis function I have, right? So I can locate these points, that is square root of E max is nothing but the signal point corresponding to symbol 1, and 0 is corresponding to symbol 0. Okay, so message point 2 in the sense here 0, symbol 0, right? Now vector is, I mean the transmitted signal is S of t. At the receiver it get affected by noise, and due to noise the signal will be x of t. X of t will be passed through a matched filter, and the output of matched filter will be sampled every t sub b, and it results in a random value, random number called x1, right? Now this x1 is a sample value of a random variable x1, right? It's a random variable x1, I mean sample value of a random variable x1. Now this x1 can fall anywhere in this region, right, in this signal space. Now we can call this x1 as observation vector. Observation, this is also a scalar observation vector. Now if x1, right, has to be decided in favor of symbol 1, what we require is this x1 should fall near to the symbol 1 point. If x1 has to be decided in favor of symbol 0, this x1 has to fall near to the symbol 0 point, right? So for that we divide this vector space into regions. Region, that is region for symbol 1 and region for symbol 2. I name these two regions as Z1 and Z2, right? Now, if the symbol x1, right? So where I mean the midpoint is square root of E max by 2, right? So if at all the signal x1 has to be decided in favor of symbol 1, what we require is this signal x1 must be greater than by 2. X1 must be greater than greater than greater than square root of E max by 2, so that you decide in favor of symbol 1, right? Now if at all the symbol has to be decided in favor of 0, what is required is it has to be, right, the x1 has to be less than x1. X1 has to be less than Emax by 2 and must be less than minus infinity, so that you can decide in favor of 0. Now there is a possibility that the transmitted symbol is 1, right? There is a possibility that transmitted symbol is 1, but it may fall inside the region corresponding to symbol 0, right? So receiver ends up in deciding in favor of 0, right? If you have transmitted symbol 0, but due to noise at the receiver, this signal falls along the along the pi1 axis and falls in the region corresponding to symbol 1. Receiver ends up in deciding it as a 1, right? So that leads to an error. Now we have discussed in the last class, right? There are two kinds of error, right? Symbol 0 is sent, but it falls inside the region Z1, and the receiver decides in favor of symbol 1, and that causes an error, right? Symbol 1 is sent. Second kind of error is symbol 1 is sent, but it falls inside the region corresponding to symbol 0. The receiver ends up in deciding in favor of 0. That means that is causing an error in the PCM system at the receiver. So received symbol will be in error due to noise, right? So this is what we have to evaluate for PCM. PCM, pulse code modulation, binary encode pulse code modulation, can be evaluated by means of error rate, or we call it as probability of error. So how we can evaluate probability of error? So we define something like, so you can see this x1, x1 is a received sample obtained by, right, 0 to t sub b x of t pi 1 of t. X1 is a sample value of random variable x1, in Gaussian random variable with mean depending on the transmitted symbol and variance equal to n naught by 2. Now you can see we can define the likelihood function for x1, right? It's a conditional likelihood function or conditional probability density function we can define. Now if 0 is sent, right, if 0 is sent, the likelihood function corresponding to 0, that is likelihood function for x1 corresponding to 0, is f of x1, right? F of x1, x1 given 0, 0 sent equal to 1 by pi n naught into e to the power minus x1 square by n naught. Why it is a minus x1 square by n naught? Because the mean of the symbol sent, right, Sij or S21 is 0. Now the likelihood function corresponding to symbol 1, when 1 is sent, we said conditional probability density function when 1 is sent, that is x1 given 1 is sent, it is nothing but 1 by square root of pi n naught into e to the power minus x1 minus minus square root of Emax by n naught whole square. Why this square root of Emax? It is nothing but the mean value of the symbol 1 sent, or a mean value of the random variable x1 when 1 is sent, or it is nothing but the actual value or actual amplitude of the signal 1. Okay. Next, so we can define the probability density curve. So let us go for to find probability of error when a 0 is sent. That is nothing but error of first kind, right? Probability of error when 0 is sent. Now this is nothing but the conditional probability of error when 0 is sent. That means what? 0 is sent, but the symbol will be received x1 which is falling in the region corresponding to Z1, I mean symbol 1, right? Probability of error, you send 0, but it will be decoded as 1, right? So what is the probability error? So we can calculate this by means of probability of error. Probability of error when 0 is sent is nothing but, you can see this probability density curve, right? Conditional probability density curve when 0 is sent, right? So mean is here, mean of the random variable x1 is here, and it is a probability density Gaussian random variable having the PDF curve something like this, and you can see the curve crossing this square root of Emax by 2 and going till x1 reaches to infinity. Now what is the probability of error? Probability of error is the area of the PDF curve crossing in the region corresponding to, falling in the region corresponding to symbol 1. So we can define probability of error as, right, square root of Emax, sorry, Emax by 2 to infinity probability of x1 given x1 sent 0 dx. Okay, so what is this probability of error when 0 is sent? It's the area under the PDF curve, that is conditional probability density curve when 0 is sent. What is the area under PDF curve when 0 is sent? It is falling in the region corresponding to symbol 1. So I put the area as, I put the limits as square root of Emax by 2 to infinity. So what is fx1? What is fx1 given 0? Fx1 given 0 can be written as 1 by square root of pi n naught into integral square root of Emax by 2, square root of Emax by 2 to infinity. What is fx1 given x1 given 1 by pi n naught into e to the power minus x1 square divided by n naught into dx1. Okay, sorry, dx1 here. Okay, dx1, right? So now what I'll do to evaluate this, what I'll do, I will just substitute, say z equal to x1 divided by square root of n naught. Okay, now I'll just change the limit. Instead of x1, I'll change to z, right? So now let us change the variable rather. Let us find out the limits, right? As x1 tends to infinity, what about z1? Z1 also tends to infinity. As x1 tends to square root of Emax by 2, z1 tends to, if you substitute, right, if you substitute this, right, it will tend to 1 by 2 square root of Emax by n naught, isn't it? Emax by n naught. Now I will write conditional probability of error when 0 is sent as nothing but 1 by square root of pi into integral square root of, that is half square root of Emax by n naught, half square root of Emax by n naught to infinity e to the power minus z square dz, right? So this expression, this equation reminds you something, right? So what I'll do, I'll just multiply and divide by 2, right? This is multiply and divided by 2. Wait a second. Right, multiply and divide by 2. What is this function now? So this we have discussed, right? Now we can define this probability of error. Somewhere here I will write probability of error when 0 is sent is nothing but half. Have you come across this ERFC? What is
error function? Sir.
Yeah, error function, right? Half square root of Emax by n naught. Okay, half ERFC of half times square root of Emax by n naught. This is what we have discussed in the past about error function. I told you it's very, very important, right? So the probability of error when 0 is sent, half ERFC into half square root of Emax by n naught, and square root of Emax by n naught, right? So this is the probability of error in PCM when 0 is sent. Okay, 0 is sent. Next I move on to finding the probability of error. So similarly we can find the probability of error when 1 is sent, right? So probability of error when 1 is sent, it is nothing but the conditional probability of error when 1 is sent. So I can write it as 1 by, right, 1 by, what I can write now, 1 by square root of pi n naught integral, right, into integral what, minus infinity to square root of Emax by 2, right, into e to the power minus x1 minus square root of Emax, right, whole square divided by n naught, right. So if we evaluate, right, so if you substitute, that is, say z equal to, say, sorry, dx1, right, sorry, z is equal to nothing but say uh, uh, square root of, right, sorry, sorry, z is nothing but x1 divided by square root of n naught, and substitute as we did for probability of error for symbol 0. So we can write probability of error for symbol 1. I will leave the simplification to you. Okay, you can try that. Okay, I can write half ERFC of half times square root of Emax by n naught, right? So now the conditional probability of error when symbol 0 is sent is same as conditional probability of error when 1 is sent. So conditional probability of error when 0 is sent, probability of error when 0 is sent is also half ERFC of half times square root of Emax by n naught. Usually when we transmit binary symbols, right, so the number of symbols overall, if we say millions of symbols we keep transmitting, and number of zeros and number of ones are going to be same, or we can say the probability of symbols 0 occurred is same as probability of symbol 1. That means the PCM symbols are equiprobable, and we can write the average probability of error, average probability of error in PCM equal to probability of error when 0 is sent multiplied by so probability of error when 0 is sent multiplied by probability of occurrence of a 0, right? We can say probability of occurrence of a 0 multiplied by probability of error when 0 is sent, probability of symbol 1 multiplied by probability of error when 1 is sent. Now these probabilities, right, probability of 0 and probability of 1 are equiprobable. We call them, these are emitted by the source, right, binary source, let us say, right, these are emitted by the binary or PCM source, and we call them as equiprobable, and these symbols are equiprobable symbols, and these probabilities we call it as priori probability. You have heard of posteriori probability. This is called priori probability. Priori probability is the probability of symbol when symbol is emitted by the probability of a symbol emitted by the or to be emitted by the source. Okay, so this is called priori probability. So probability 1, and they are equiprobable. They are equiprobable. Half times PE of 0 plus half times half times PE of 1, and probability of error in PCM is nothing but half times ERFC half square root of Emax by n naught. Okay, so this is the expression for probability of error, right, of a PCM system. Right, now you have come across this ERFC function. What this ERFC function is? As So ERFC of you have seen the table, right? ERFC of you, as u increases, what will be the case? ERFCU decreases, right? Very small increase in u. If you go through the table, you find very small increase in u will lead to drastic decrease in ERFCU. And we have seen the approximation also, right? It is e to the power minus u square. You can see e to the power minus u square means it is quite exponentially decaying, right? So a very small increase in u will lead to very large, very small increase in u will lead to drastic decrease or fall in ERFC of u. Okay, so what this represents? This represents Emax, square root of Emax by N naught. Emax by N naught. Emax by N naught is nothing but signal energy to noise power spectral density ratio. Signal energy to noise power spectral density ratio. Now, if you want to reduce the probability of error, decrease the probability of error, what you require to do, you have to increase this signal to noise power density ratio. So noise power density, noise power spectral density is not going to change, but you have to increase the signal energy, right? You have to increase. How far you can increase? You cannot increase to a level you want, but there is always a limitation. You can increase up to that and see that you have for a noise, for a particular noise, you have a very high energy that can lead to very low probability of error, and your PCM will be highly efficient, right? So we need to see that this Emax by N naught has to be at the higher side so that the probability of error is very, very low, right? More you increase the signal energy, lesser will be your probability of error. Okay, so now we have just done this, right? As far as PCM system is concerned, this I have combined all three figures together, right? So one showing figure A is showing your signal space diagram, and figure B is showing the conditional probability density function for a symbol 0 when 0 is sent, and the third figure C is showing the likelihood function or the plot of a likelihood function when symbol 1 is sent. Okay, so now let us try to represent the signal energy in terms of power. So we can write Emax as P max into T sub B, where P max is power, right? Peak power of the signal, right, is nothing but joules per second. So Emax can be written as P max into T sub B. Then we can write the signal to noise ratio, that is signal energy to noise power spectral density ratio. This is signal energy to noise power spectral density ratio in terms of signal to noise power ratio, right? Emax by N naught equal to P max into T sub B by N naught, right? Now if I take this T sub B in the denominator like this, it will be, right? So P max is nothing but the signal power, and this N naught by T sub B will be noise power or noise variance, noise variance. Okay, representing noise power. Noise variance is a noise power, that is N naught by T sub B is a noise power. So now this P max by N naught by T sub B is signal to noise power ratio. Signal to noise power ratio, right? More this signal to noise power ratio, less will be the probability of error, right? So we have to have more and more signal energy or signal power has to be increased, so that we will have very high signal to noise ratio. Very high signal to noise ratio will lead to very low probability of error. Let me just go through performance evaluation of pulse code modulation system. You can see the x-axis corresponding to the signal to noise spectral density ratio, right? It starts from say 0 dB, 10 dB, 15, 20, and so on. and you can see y-axis is showing the probability of error. Now you can see for very low signal to noise ratio around say 10.5 dB or 10.5 dB, you can see the probability of error is very high, 10 to the power minus 2. And as you keep on increasing, you find the probability of error. If you see this signal to noise ratio is crossing 20 dB, will lead to the probability of error very, very low, right? We may not be permitted to use this signal to noise ratio, right? We may not get permission to use the power in such a way that we'll get this 20 dB, but as long as we can keep the probability of error below 10 to the power minus 6, our system will be very, very efficient. So we expect the probability of error be below 10 to the power minus 6, or we should have our signal to noise ratio around 17 dB. So you can take this 17 dB as a threshold for better, performing PCM system. So we should have the signal to noise ratio around 17 dB to have very low probability of error. Like let us see a table in which for different signal to noise ratio, how the error will get if affected, right? How PCM will get affected. Now you can see for a bit rate. So you can see this table. This table I have taken from Simon Hakin, right? So you can see for a bit rate of 10 to the power 5 bits per second, right? And if I use the signal to noise ratio around 10 dB, right? The formula here uses not a error function table, ERFC table. ERFC of u is measured like e to the power minus u square divided by square root of pi into u, right? Square root of pi into u, okay? Right. So this formula is applied here. Now for a bit rate of 10 to the power 5 bits per second, if the transmission rate is 10 to the power 5 bits per second, right? We can define the probability of error for different power ratio, that is signal to noise ratio. For a signal to noise ratio of 10.3 dB, right, the probability of error will be around 10 to the power minus 2. That means for a bit rate of 10 to the power 5 bits per second, every 10 to the power minus 3 second, there will be a 1 bit error. So 1 bit error occurs every 10 to the power minus 3 second. How you can calculate this? 10 to the power 5 into 10 to the power 5 into 10 to the power minus 2 will lead to 10 to the power 3. So 10 to the power 3 bits are in error. That means every 10 to the power 3 bits per second are in error. That means every 10 to the power minus 3 second there is 1 bit error, right? Similarly, 14.4 dB will lead to the probability of error 10 to the power minus 4 and will lead to error every 1/10 of a second there is an error, okay? And 16.6 dB 10 to the power minus 6, so you will get approximately 1 bit error every 10 seconds. After every 10 seconds you have 1 bit error, right? 18 dB if it is, you will get error every 20 minutes, 1 bit error every 20 minutes. 19 dB, 1 bit error every day. And if it's 20, you can see just a small increase in dB has reduced the probability of error, and also you can see you will get error approximately once in every bit error, that too bit error once in 3 months, okay? Right? I hope it is clear to you. Yeah, we'll take one example. So the example is taken from Simon Hakin, bit 5.2.1, a binary system using on-off signaling. What is on-off signaling? Unipolar NRZ, just we discussed, okay, whose analysis we have seen, operates just above the error threshold with an average probability of error equal to 10 to the power minus 6. Average probability of error equal to 10 to the power minus 6. Suppose that a filter bandwidth at the receiver input is doubled. Find the new value of the average probability of error. Find the new value of average probability of error. So what is the error function corresponding to, or the probability of error corresponding to the PCM wave? It is nothing but half ERFC of half times square root of E max by N naught, or it is nothing but, in terms of power, if at all I have to write half ERFC half times, right? If I have to write this, P max divided by N naught by T sub B. Now T sub B is the bit rate, okay? Bit rate, right? In a which is telling the bandwidth of the symbol, and in a bandwidth of the symbol, right, it defines the noise power, right? N naught by T sub B, half ERFC, right? It is nothing but what? It is given as P, probability of error is 10 to the power minus 6, right? 10 to the power minus 6, right? 10 to the power minus 6. Now, what is this U then now, right? So 10 to the power minus 6 is the given probability of error, right? Given probability of error. Then we can say ERFC of half P max. I'll just take a break for a few minutes, okay? I have to attend one very important call. I'll just take a break. Yeah, I'm sorry. I was very, I had to attend one call. Are you able to hear me? Are you able to
Yes,
hear me?
sir.
Yes, sir.
Right. So now it is P max by, sorry, N naught by T sub B, right, is equal to 2 times 10 to the power minus 6, right? 2 times 10 to the power minus 6. Now, what this value, half square root of P max by N naught by T sub B, how we can find from this error function, right? So that this value, I mean, ERFC of this value will lead to 2 into 10 to the power minus 6. How we can do that?
Excuse me, sir. Excuse me,
Yeah.
sir.
Yeah.
Sir, in the question it says that the filter bandwidth at the receiver input is doubled.
Yeah.
So, sir, shouldn't we manipulate the TB of this function?
I will manipulate it later, but let me find the value of U, okay, ERFC of U, so that I can manipulate it. Okay, right? How do I find it?
Sir, but I don't get why we are doubling the probability.
See here, binary PCM system is there, on-off signaling. The probability of average probability of error is 10 to the power minus 6 as per this expression, right? ERFC of U. Okay. Suppose at the receiver, bandwidth of the receiver input is doubled. Now, if the bandwidth of the receiver is doubled, so noise, noise power spectral density is n0 by 2, which is existing from minus infinity to plus infinity, right? Yes or no?
Yes, sir.
Yeah. Then noise power in a bandwidth of 1 by TB is noise power in a bandwidth of 1 by TB is this one, right?
Yes, sir.
I double the bandwidth means
Double the bandwidth TB by 2.
not TB by 2, 2 by TB.
Yes, sir. 2 by 3.
Okay, 2 by TB. Now the bandwidth will be doubled, so noise power will be doubled here. That I will not include here now, not to confuse you. I will not include now here. I will include it later. Okay. So how do I find it? First, I need to find this this value so that I can make out the probability of error when it is getting doubled, when it gets doubled, right? So this is 2 into 10 to the power minus 6, right? Right. So who can give me this ERFC of this is nothing but ERFC of u. Right, so this is ERFC of u telling me it is 2 into 10 to the power minus 6, right? But how can I find out u? I can find it out from where?
Table.
Yeah. Let us see where I can find this 2 into 10 to the power, I mean minus 6, right? So where can I find out?
3.36.
3.36, right? 3.36 is the one which can give me around 2 into 10 to the power minus 6, right? Yes or no? Right. So therefore half times square root of P max by n naught into T sub B is nothing but what? 3.36, right? 3.36, right? Now what is given in the problem? Find a new value of the average probability of error if the bandwidth at the bandwidth of the receiver filter is doubled, right? Bandwidth of the receiver filter is doubled. Now noise power spectral density is n0 by 2, right? Now if I see the noise power spectral density is n0 by 2, right? If the signal bandwidth is right, signal bandwidth is 1 by T sub B, what will be the noise power spectral density I have to take? Right? No, I mean what will be the noise power? Noise power will be equal to, I just take the area under this curve, right? So area under this noise power spectral density, it is nothing but n0 by T sub B, right? n0 by T sub B will be the noise power for me. Yes or no? Right? Area under this noise power spectral density, area under the bandwidth, right? Now if I double the bandwidth at the receiver, this is noise power spectral density for me. I get double the bandwidth, right? Double the bandwidth, 2 by T sub B minus 2 by T sub B, right? It will be something like 2 times n0 by T sub B, right? Sorry, I'll not do it here. Right? If the bandwidth at the receiver, filter doubled, then so the noise power will also be doubled, right? So this signal to noise ratio will also be doubled, right? The signal to noise ratio will also be doubled. That means I have to change my signal to noise ratio, right? P max by n naught by TB, right? To be multiplied by or to be divided by square root of, sorry, to be divided by 2, right? To be divided by 2. It is inside the square root. Okay. That means what I have to do it on the right hand side? What I have to do on the right hand side?
So divide by square root of 2.
Square root of 2. What it leads to? Around 2.37. Now, therefore, what is the probability of a new probability of error? New probability of error. I'll name it as new, right? New probability of error. Probability of error dash. What will be it? Again, what I have to do? What I have to do again? Hello.
So
Sir,
what did
use
we
the
multiply?
table.
ERFC table.
Yeah. Yeah. What I
So
have to
use
do?
the ERFC
Why it
table
is
to
multiply? See
find
here, I am as good as multiplying here this whole thing, whole thing by 1 by root 2. Right? On the left hand side here, you can see this whole thing I have multiplied by 1 by root 2 because the bandwidth is doubled. That means what I have to do? I have to multiply by 1 by root 2 on the right hand side also. It leads to 2.37. What is the probability of error? How can I find probability of error again?
Sir, it will be half ERFC of 2.37.
No, this. See, 3.36 is this actual value I get from this I get. Now if I multiply by root 1 by root 2, I'll get 2.37. What will be the new probability of error? So what I new probability of error? 2.37. I have to look into 2.37.
Sir, what it would be half ERFC of 2.37.
It is nothing but 0.8 into 10 to the power minus 3, right? Around approximately, so it will be 0.8 into 10 to the power minus 3, or I can say more approximately it is 10 to the power minus 3 is the probability of error. Any doubts here? Yeah.
Excuse me, sir.
Yeah.
Probability of error is half times ERFC of 2.37, right?
Yes. This whole thing is nothing but 3.36, and this whole thing is nothing but this, and this whole thing is nothing but 2.37. Right? I have not touched 1 by 2 here. I have not touched at all. I have not.
Yes, sir. My doubt is that here the U value is 2.37, right?
Yeah.
Yes,
U
sir.
value is 2.37.
So
But
we
when we
have
put
to.
it above,
Yeah. I'll just take it. 2.37, not ERFC of U, whole thing, right? Whole thing, half into square root of V max by V naught by TB. Okay. ERFC of U, whole thing. Okay.
So,
Fine.
sir, the lookup of the table, this 0.8 into 10 minus 3 is ERFC of this value, 2.37, right?
ERFC of this new U. Okay, new U, because bandwidth is doubled.
Yes,
Okay,
sir.
bandwidth is doubled, noise bandwidth gets doubled, it leads to increase in probability of error.
yes,
Okay.
sir, but the average probability is half times ERFC of U, right? What we have calculated is ERFC of U.
Yeah, 1 second. Half times ERFC of U. Okay, 2.37. Probability of error is half times ERFC. Yeah, half times ERFC of this whole thing I have calculated, right? So then new probability of error, 2 into 10 to the power minus 6 I got, right? So just divide this by, isn't it? Just divide this by
Half.
half or 2.
Yes, sir, divide by 2.
Divide by 2. Okay. Divide by 2. 10 to the power minus 3 by 2. Okay. New probability of error is 10 to the power minus 3 by 2. Okay. Right. Next example. This is 5.2.2. Consider a binary PCM system that uses. Just remind me around 4:20. The time is up. Okay. Otherwise, I'll not be able to make out. You will have to write a test, no? Okay. Yeah, the next problem is 5.2.2 of your Simon Heckin book. Consider a PCM system that uses polar signaling with symbol 1 and 0 represented by plus a by 2 and minus a by 2 respectively. The receiver shown in figure 5.6. This 5.6 figure is nothing but the one which we have. This, okay, this is the receiver. Okay, this is the receiver. PCM wave. This is the receiver, which is same what we have done for unipolar probability of error. So now it is polar probability of error we need to find out, right? So now let me read it again. Consider a binary PCM system that uses polar signaling with symbols 1 and 0 represented by plus a by 2 and minus a by 2 volts respectively. That means plus a by 2 for symbol 1 plus minus a by 2 for symbol 0. The receiver is shown, you have seen, okay, where the additive noise WT is the sample function of a Gaussian process with 0 mean and the power spectral density n naught by 2. Calculate the average probability of symbol error in this method of signaling. How you follow it? How you start solving this? Right, the signaling is polar NRZ format. Now if I take signal S1 of t, it is a polar NRZ format, right? The duration of this symbol is t sub b, amplitude is a by 2, and S2 of t is nothing but for symbol 0, duration of the symbol is again t sub b, but the amplitude is minus a by 2. Okay, right? So symbol S1 of t, that is symbol 1, and this is for symbol 0. Okay, symbol 1 S1 of t, symbol 0 for S2 of t. Okay, now how I can represent this S1 of t and S2 of t as a linear combination of n orthonormal basis function? Right, I can write this S1 of t. How many basis functions do you think you have for this? S1 of t can be represented as square root of E max, right? E max by t sub b, right? For a duration of 0 less than or equal to t less than or equal to t sub b, right? So what is energy of this signal? What is the energy of the signal S1 of t?
A
What is
square
E
by
max?
4 TB.
Yeah?
A square by 4 into TB.
A square by 4 into t sub b, right? Similarly, S2 of t, or I can write this first, S1 of t is nothing but a square, right? Or square, sorry, a square by 4 into t sub b whole divided by square root of t sub b, right? Divided by square root of t sub b, right? For a duration 0 less than or equal to t less than or equal to t sub b, right? So where S11 here is nothing but I can write a by 2 square root of tb, agree? And phi 1 of t is nothing but square root of 1 by t sub b, 0 less than or equal to t less than or equal to t sub b. Similarly, S2 of t can be written as S2 of t can be written as a square by 4 t sub b divided by t sub b, and here for a duration, right, 0 less than or equal to t less than or equal to t sub b, and S21 is equal to, sorry, here minus, right, minus S21 is equal to minus, sorry, minus a by minus a by 2 t sub b, and phi 1 of t again is, there is only one basis function, right? Square root of 1 by t sub b, 0 less than or equal to t less than or equal to t sub b. Shall I leave this problem on your head so that you can get the error function for this?
No, sir.
Why? You don't want to try?
Excuse me, sir.
Yeah.
Here the energies of the signal is same, so
Yeah.
the probability functions will also be same, right?
Probability functions in the sense error function you want to say? Yeah.
Yeah, 1 by root pi and not that function is gonna be same.
Yeah. Probability of error when 0 is sent, probability of error when 1 is sent, and it is the average probability of error provided the symbols are equiprobable. Obviously symbols are equiprobable, and we can write the error function as, can you try? You will try, I'll just write the answer. What do you think the error function, I mean the probability of error will be? What will be the signal space? I will just write it later. Okay. So what is the signal space representation? 1 point at representing 0, symbol 0, okay, minus
a by 2 to be
a by 2
root TB
root TB. Other one is at
plus a by 2.
plus a by 2 root TB. And
Sir,
at the center we have,
sir, in the left side you haven't written root TB in the S21 function.
oh yeah, thank you for reminding. Okay, now this is what the decision boundary region corresponding to symbols received falling in this region are decoded as 1, and in this region Z2, if it all symbol is falling in this region, it will be decoded as 0, right? Yes or no? So there are errors of the two kinds, right? Probability of error you can find, right? You can see the mean value of the conditional random what do you call probability density function, or rather the signal received signal x1, which is a sample value of random variable capital X1, has a mean minus a by 2 square root of TB if symbol 0 is sent, and it is a by 2 into TB root TB if symbol 1 is sent, and the noise variance is n naught by 2. Okay, right? The probability density curve, PDF curve, looks like this, right? The error of the first kind for symbol 0, right? 0 to infinity, right? So you can find this. You will find it, no? Just simple mathematics it is. I will write the expression. Okay. Okay. I'll write the expression for probability of error. Hello. Are you there?
Yes, sir.
Are you there? Hello.
Yes, sir, we can hear you.
You can find the expression. No, I will write, but you can try this at home, and you can write. Now, probability of error can be defined as half ERFC of a by 2 square root of TB by n naught. Okay, so this is the probability of error of a PCM if binary encoded signals are polar NRZ format. Okay. Hello. Hello.
Yes, sir.
Hello.
Yes, sir. It's visible.
At least you will do that, no?
Yes, sir, we will try.
Okay. So this expression I have written, you have to get this expression, that's all. If not, if you don't get this expression, just catch me again. Okay. In the next class. Okay. Right. So the average probability of symbol error The answer to this question is this. Okay? Fine?
Yes, sir.
Oh,
Yes, sir.
you are there, no?
Yes, sir.
Yeah. The next problem based on this only. A continuous time signal is sampled and then transmitted as a PCM wave. The additive noise at the input of the decision device in the receiver has a variance of 0.01 volt square. That means it is noise variance is nothing but representing a noise power. Okay, 0.01 volt square. Assuming that is bit A, assuming the use of a non-return to zero polar signaling, determine the pulse amplitude that must be transmitted for the average rate average rate not to exceed 1 bit in 10 to the power 8 bits. That means what average probability of error must be less than 10 to the power minus 8. Okay, and the second bit, if the added presence of interference causes the error rate to increase to 1 bit in 10 to the power 6 bits, what is the variance of the interference? Okay, let us see the first bit. Okay, so what is the expression for error function there? Probability of error, average probability of error is half times ERFC A by 2 square root of TB by N naught, right? Right, the probability of error, the probability of average probability of error is nothing but half ERFC of A by 2 square root of TB by N naught, right? TB by N naught. Or I can even write this again, half error function A by 2, right? A by 2 into square root of 1 by N naught by TB, right? Right. So what this N naught by TB represents? N naught by TB represents
Noise power.
noise power, right? So this is nothing but what given bit A 10 to the power minus 8, 10 to the power minus 8, or therefore I can write ERFC, right? ERFC, right? ERFC. What is required to be found here? Assuming the determine the pulse amplitude. What we have to do? We have to determine the pulse amplitude. Okay, what we have to determine? We have to determine A, right, or A by 2, right? Pulse amplitude, that is half. I will take this inside ERFC square root of A square by 4 divided by, what is N naught by TB then? It is given as 0.01, right? 0.01. Yes or no? 0.01. Yes or no? Right? 10 to the power minus 8. Or, sorry, probability of error. Or it can be further written as, so this I can write ERFC of, I can write this, I can remove this whole square root. I can write this as A by 0.2. Can I write like this? A square by 4, 4 goes down, 0.04, square root of A square by 0.04 is A by 0.2. Is it okay? Is it
Yes, sir.
okay?
Yes.
Now, the problem here is 2 into 10 to the power minus 8. Is it possible to find the probability, find U, that is A by 0.2 using the error table, ERFC table? Is it possible? ERFC table will not give me that, yeah, will not give me that value. So what I'll do, I'll use the approximate formula. formula for ERFC. What is that? ERFC of u, approximate formula for ERFC of u is nothing but e to the power minus u square divided by square root of pi into u, right? Yes or no? Yes or no? Hello.
Yes, sir.
So e to the power minus u square divided by square root of pi into u is nothing but what? 2 into 10 to the power minus 8. Okay. What is u? What is u? U is nothing but
A by 0.2.
a by where? In this case, u is nothing but a divided by 0.2. A divided by 0.2. Now, how you can find simplify this? You can take a log, I mean natural log, and find simplify this, right? Simplification I can leave it on you. Okay. Answer I will write. Okay. So therefore, what is a? A is, as per my calculations, you can simplify this, no? If the equation is something like this, okay, you can simplify this A.
So is it
Yeah.
u is equals to 3.97?
U is not U. Yeah, 3.9683 I got.
Yeah, okay, sir.
Yeah, fine. So first let us find U. What is this? I mean ERFC. Okay, this whole thing, sorry, not this. 3.9683. Sorry, 9683 is U. Sorry, e to the power minus u square divided by root pi into u, right? 3.9, not 2 into 10 to the power minus 8, right? E to the power minus u square divided by root pi u.
Sir,
Sorry.
how did we get the u as this?
Sorry. Yeah.
Sir, I
What is
think first condition
2
was
into 10 to
correct.
the power minus 8? 2 into 10 to the power minus 8 is probability of error, right? Right. So probability ERFC of sorry. Yeah. I will do it again. ERFC of u. So this ERFC of a by 0.2 is as good as 5a, right? Is nothing but 2 into 10 to the power minus 8. Okay, 2 into 10 to the power minus 8. Right. This is also equal to, right, e to the power minus, right, 5a square divided by root pi into 5a. Okay. Root pi into 5a, right? So now you take this e to the power minus 5a whole square, okay, minus 5a whole square equal to 2 into 10 to the power minus 8 into 5a into root pi. Okay, take a natural log both sides, okay, and simplify. If you take natural log both sides, right, you take natural log both sides, what you will get? What you will get? Natural log of e to the power minus pi a square into equal to natural log of 2 into 10 to the power minus 8 5a into root pi. I thought you will do it. That is why I am not able to find the right steps which I have done here. Okay. 0.2. Yeah. So take natural log, and what you will get, this whole thing, actually I did by using MATLAB function ERFC of inverse. Okay, ERFC of phi a is equal to 2 into 10 to the power minus 8 I got. Okay, and the amplitude, yeah, hello, any answers?
So,
Yeah,
sir, so for the U value, I got it as 3.9014
3.9014.
U,
I
as in
got it
5 wave.
as 3.9683.
Sir, I'll check.
Yeah, okay, no problem. 3.90 will also do, right? Now, what is the value of A? Value of A. So you got U is equal to 3.9683, right? So U is nothing but what? A by zero point 0.2 is equal to 3.9683, right? What is A? What is A?
So 0.793.
Yes. So 0.7 I got 0.7937. Even 79 will do, not an issue. 0.7937 I got. Okay. A equal to 0.7937. Now the second bit, if the added presence of interference causes the error rate to increase to 1 bit every 10 to the power 6, right? So what will be the variance of the interference, right? So added in presence of interference causes the error rate to increase to 1 bit in 10 to the power 6 bits, right? That means I can rewrite this probability of error expression, probability of error, as nothing but half times ERFC, right? ERFC square root of a square by 4 divided by n naught by t sub b, right? N naught by t sub b, or it is the added interference added with the previous one, right? I'll name it as sigma square, or sigma n square is the added interference. Okay, right? Sigma n square dash or sigma n dash squared, right, is equal to, what is the probability of error? 10 to the power minus 6, right? Now what is this added interference? Sigma n dash square is nothing but the actual interference. What is it? 0.01 volt square plus the added interference. Say added, I'll name it as added interference as a variance, this one, that led to 10 to the power minus 6. Okay, now what is required? You have to find the added variance as well as this, right? Can you find? Again, ERFC of square root of a square by 4 by sigma n square n dash square is nothing but 2 into 10 to the power minus 6. Now this, can we find this value, right? Can we find this value in error function table?
Yes, sir. It is 3.36.
3.36. Is it? Is it 3.36? All of you? 3.36.
Yes, sir.
3.36. Right? Sorry. So this leads to square root of a square by 4 divided by sigma n square dash is equal to 3.36. Right? 3.36. We know a square, right? We know 0.7937 squared divided by 4 divided by sigma n dash squared equal to 3.36. Squaring both sides, what do we get? Squaring both sides, we get right hand side as 11.2896, and on the left hand side what we get? Some value in the numerator divided by sigma n dash squared, right? So therefore, what is sigma n dash squared? It is nothing but 0.017 volt square. Now what is sigma 1 square n dash square actually? It is nothing but actual interference which was there plus added interference, which is nothing but 0.017. Therefore, what is the added interference? I mean the power variance of the added interference. It is 0.007 volt square. Is it? Okay. Okay, all of you.
Yes, sir.
Yes, sir.
I will just stop here. I think it's time for your quiz, right? Any doubts?
Excuse me, sir. I had one doubt. Can we just go to the previous slides in which we had written P average is equal to P of 0 into half plus half into P of 1. So shouldn't it be the shouldn't it just be? Can you just go?
Which one?
Previous slide.
Which one?
More. Before the examples.
Before the commencement of examples. Here.
It's not visible. Actually, it's in the.
Have I
can see
shared?
Yeah. This slide. Yes. So
This one only.
If we get this, so shouldn't it P of 0 and P of 1 is the same? So shouldn't we write as only, why is there the half sign? P is equal to half of ERFC. So why is that half sign? Shouldn't it be 1?
What we found in the case of probability of error when 0 is sent, see here, this expression we got here, it was actually 1 by root pi. Okay, 1 by root pi. What did I do? I just multiplied and divided by 2. That is why this function became becomes ERFC of u.
Understood, sir.
That retained half. Okay, that retained half. Whereas in the case of where here in this half won't be there, but here there will be a half. Okay, because of the error function. You just solve it again and you will come to know. Okay, 5.2.2 and even the one which I have discussed for unipolar NRZ format. Okay, any more doubts, please?
So what is the duration of exam?
So you will be known, I think, half an hour.
So it starts at 4:30.
Yeah, 4:30 it starts. That's
Okay,
why I'm
sir.
stopping now. Wait a minute. Don't leave. Don't leave. Let me take the or download the attendance. Yeah, you can leave now. Okay. We'll
Thank
meet
you,
on
sir.
Thursday and continue from where we stopped. Okay. All the best.
Thank you, sir.
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 Yeah.
Thank you, sir.
Yeah.